Okay, we're going to work through problem 1.6 from your textbook, which is a nice short review problem that goes over ideas of units and dimensions and some basic concepts like density and weight. So the problem says that you've got this tank, and inside the tank there's air. So the tank is filled with gas, it's filled with air, okay? And it's pressurized, and the pressure inside the tank is shown by this gauge here. Its pressure is 680 kilopascals. And we're also told that the temperature inside the tank is 70 degrees Celsius. It's pretty warm. Also told that the tank has a volume of 1.35 cubic meters. So the question is, what is the weight of the air in the tank at that temperature and pressure? So we're asked to basically compute the weight. So I use the notation W, capital W, to represent the weight. Okay, so now we can just review some of the basic concepts covered in the chapter. One is that we know that weight is just equal to mass times gravity. Okay, when we have a liquid, the mass is just equal to the density of the fluid, density of the fluid times the volume. So mass is just the density of the fluid rho times the volume v. Okay, so now we have the weight of this gas, of air, being the density of the air, volume of the air times g. And the last piece of the puzzle here is relating the density to the pressure, the temperature. And that's done through the ideal gas law. So pressure is equal to rho times R times T. So pressure equal density times the gas constant times temperature. Key thing here is that the gas constant R in this form will depend on the gas. For air, when you're working with air, R is equal to 287 joules per kilogram per Kelvin. A joule is a Newton meter, and a Newton is a kilogram meters per second squared. So we can also think of the units here as kilograms meters per second squared times meters, which gives us meters squared, divided by kilograms divided by Kelvin. And you'll see there that the kilograms will cancel, and you're left with meters squared per second squared per Kelvin. Okay, so helpful just to kind of keep track of those units. So now we can rearrange this expression for rho. We can say that, well, density is just going to be equal to pressure over RT. And so if we substitute this expression into this expression, that tells us that the weight, W, will just be equal to P over RT times volume times G. Now we're ready to substitute numbers. We've solved the problem first analytically, and now we're ready to substitute numbers, and in the process we'll also want to pay attention to the units to make sure that the units work out correctly. Okay, so we'll go ahead and put our units in. We're going to have 680,000 pascals, which is newtons per meters squared. Okay. We're going to multiply by the volume, which is 1.35 meters to the third. We're going to multiply by G, which is 9.81 meters per second squared. And we're going to divide by R, which is 287 meters squared per second squared Kelvin. And we're going to divide by T, which is going to be 70 degrees Celsius plus 273 Kelvin, which is the baseline. So we end up with 343 Kelvin. My pen is dying, so I'll try another pen. Okay. So if we work through the numbers, this works out to be 91.5. Do all these calculations. The bigger question is, and the question that you want to, that will show that you did this properly, is whether the dimensions work out correctly. So let's check the dimensions. They're a little messy here. First of all, we've got Kelvin over Kelvin, so Kelvin is going to cancel out. We're good there. We have second squared in the denominator here, and second squared in this denominator here, so those are going to cancel. We've got meter squared in the denominator, meter squared, that's meters to the fourth. We have meters to the cube, and another meters here, that's meters to the fourth. So these dimensions all cancel, and all we're left with is 91.5 newtons. Okay, so now we were asked for a weight. A weight is a force. The force works out to be 91.5 newtons, and we have a degree of a check here that's based because our units worked out properly. So here what we've done, just to review, is we've used the ideal gas law to come up with an expression for the density. That then expression for the density is substituted into an expression for the weight. The weight's based on mass times G, and working through the numbers, we get a weight of 91.5